Okay, in this lecture we're going to do a continuation, which is more proof by contradiction. The only thing that's specific to this lecture is the statements we're trying to prove will be if-then statements. As you know, most theorems are if-then statements. Okay, so I want to remind you of the outline for proof by contradiction. Okay, so the outline is that you have a proposition let's just call it P, okay, and in your proof you start by supposing the negation of P, and then you work your way into a contradiction. Okay, and so thus the negation of P is false because it brings about a contradiction, and therefore P is true. Okay, that's the outline. Now, in today's lecture, we are specifically going to look at examples where the proposition that you're trying to prove is a conditional. So what if P was something like A implies B? Then you would suppose the negation of that. Now, you guys are doing pretty good on this. The negation of a conditional. A lot of people get this wrong, but in this particular class, I remember on the test, you guys actually are picking it up pretty well. The negation of A implies B is a conjunction. It is A and not B. Okay, so what I'm saying is that if you're trying to prove A implies B, then if you want to do a proof by contradiction, then what we do is we start off by assuming or supposing A and not B. I wrote supposing. I should have just written the word suppose. Okay. So you suppose A and not B. You derive a contradiction. Thus, A and not B is false. Therefore, A implies B. Okay? Now, just for the sake of comparison, let's remind ourselves about proof by contraposition. In that case, we suppose not B, and then we derive not A. Thus, not B implies not A, therefore A implies B. Okay, they're very, very similar. They are just slightly different in a subtle way. Okay? And it's not important to me at all how well you keep those two things separate. The only thing that's important is, can you accurately construct the proof? And in fact, most people don't even use the term proof by contraposition. Okay, so that is not important to me. That's just semantics. What's important to me is, can you construct a proof in a valid manner? Okay, let's get some practice with this stuff here. So we're going to do this example first. Suppose A is an integer. If A squared is even, then A is even. Okay, let's prove that. Okay, so here's A. And here's B. So we start by assuming A and not B. Okay, so let's write, let A be an integer, and suppose A and not B. So suppose A squared is even and A is not even. Now just a note about word choice. If you think it sounds nicer, then you can certainly use the word but instead of and. You could say, suppose A is even, suppose A squared is even, but A is not even. This is surprising to a lot of people, but the words and but are logically equivalent. I know we don't often use them interchangeably in the English language, but logically they are interchangeable. Okay, so if you like the sound of that better, then that's fine. You can do that. Okay, so where can I go from here? Well, if A's not even, then it's what? It has to be odd, right? And if A is odd, then what does it look like? It has to equal 2 times an integer plus 1. And that is by definition of odd. Okay, so if A equals 2 times an integer plus 1, then what would A squared equal? Algebraically, it would equal 2k plus 1 squared, which equals what? 4k squared plus 4k plus 1. And isn't that equal to 2 times 2k squared plus 2k plus 1? So what kind of a number is a squared? It would be odd, wouldn't it? Because what? Is it just because of that plus 1? Is it just because of that plus 1 and this 2? Well, it's also because this number is an integer, right? So I should say, so a squared is odd since 2k squared plus 2k is an integer. Okay. Well, isn't that a contradiction? Because I've already said up at the top that a squared is even. And now I've got a squared is odd. Don't those two things contradict each other? So let's point that out. This contradicts the fact that a squared is even. And that's our contradiction that we derived. Okay? So therefore, if a squared is even, then a is also even. Okay? You don't have to put the word also in there. That's not a logical word. So that's how that works. So we had if A, then B. So we suppose A and not B. And then we derive some sort of a contradiction. And that allows us to conclude that A implies B. Okay? That's how that works. Let's do another one. If A and B are integers, and A is equal to or greater than 2, then A does not divide B, or A does not divide B plus 1. Okay, let's work out a proof. Now, the way it's currently worded, you would probably say, here's our if, the hypothesis, and here's our then, the conclusion. And that's fine. It's not the way I would do it if it. To be honest with you, what I would do is I would say, let A and B be integers, period. And I would fix that as a fact. And then I would say, here's my hypothesis, and the yellow is my conclusion. But because that's not the way it's written, I will work with it the way it's written. Okay? So the green is the hypothesis, the yellow is the conclusion. And so we want to start by assuming the negation of if green, then yellow. So that means we suppose green and not yellow. So suppose a and b are integers and a is equal to or greater than 2, and it is not the case that a does not divide b or a does not divide b plus 1. Okay? Now look in there, you see I have two ands that follow almost one right after the other. Personally, that's a situation where I would like to throw in a but instead of an and, just to make that sound not so repetitive. Okay? All right. Well, let's look at this part. It is not the case that a divides b or a, does not divide b, or a does not divide b plus 1. Okay, then what? So in other words, what I'm trying to ask you is, we have this. That's what we're looking at. Okay, what can I say from that? Doesn't De Morgan's law tell me not a divides b and not a divides b plus 1? Isn't that De Morgan's law? So let's write that down. So we say then it is not, I keep saying divides when I mean to say does not divide. I apologize for that. Okay, so then it is not the case that a does not divide b. Okay, let me stop there and ask you a question. I think we can erase this gray stuff now. There's more to that sentence, okay? I'm stopping to ask you a question. Is there a shorter way of saying this? It is not the case that a does not divide b. That's a double negative, right? I'm saying a does not divide b. Isn't there an easier way of saying that? Isn't it the same thing as saying a divides b? Boy, that would be way shorter, wouldn't it? So instead of saying it's not the case that a does not divide b, we can simply say a divides b. Okay, that is the negation of that. Okay. And the or turns into an and because of De Morgan's law. And then I write the negation of this. A divides b plus 1. Okay, and why is that? That's by De Morgan's law. And I should state that because I don't think it's necessarily obvious what we just did. And so I want to put the reasoning there so the person reading it says, oh, they used De Morgan's law. Okay, now I understand where they got that from. Because that person would look at the previous line and say, oh yeah, here we have the negation of a disjunction. And De Morgan's law gives you the conjunction of the negation of these two things. Okay? All you should need to do is point out that you used De Morgan's law, and then the reader should be able to figure out how you got that. Okay? Now, what does it mean to divide? The definition of divides says that if a divides b, then b equals a times an integer, right? So hence, b equals a times some integer. And also, let's go ahead and point out that b plus 1 would equal a times an integer as well. Not necessarily the same one, so we have to give this one a different name. Okay, and we need to point out that those are integers. Okay, and why is that true? That is by definition of divides. Okay. Now, if b plus 1 equals AD, then doesn't that mean that b would equal AD minus 1? So can't we say now that thus, look at this, AC equals B, and B would also equal, besides AC, it would also equal AD minus 1, right? Where can we go from there? And then I can say, so A times D minus C would equal AD minus AC, which would equal what? Look at the previous line. AC is AD minus 1. So let's put that in. And what do we end up with at the end? We end up with 1, right? So A times DC equals 1. Now, what do we know about A? It's an integer, and it is at least 2. So that means A is a positive number. And if A times D minus C is positive, and A is positive, then what can you tell me about D minus C? Wouldn't that have to also be positive? A positive times something equals a positive, then that something has to also be positive, right? Okay, so since A is positive and A times D minus C is positive, how do I know it's positive? Because it equals 1. Then I can make the conclusion that D minus C is positive. And furthermore, I can also say that A equals 1 over D minus C. Just again, going back to this, A times D minus C equals 1. Okay? And what is D minus C? It's an integer, and it's positive. Okay? So A equals 1 over a positive integer. Let's shrink this down a little. Okay, so A equals 1 over DC, where, I said DC, I meant D minus C, where D minus C is an integer, and D minus C is greater than 0. I'm not adding anything new here. I'm just repeating some things because I'm wanting to tie together 3 different things. Okay, I'm tying together this and this and this, that c and d are integers. So d minus c is an integer. So 3 things from various points along the way, and I want to now tie those all together. So I'm just putting in one line where I'm just pointing out again 3 things that I already knew, and I'm just pointing them out together in one location. Okay? Because together those 3 things tell me that A is equal to or less than 1, isn't it? Think about it. A equals 1 over a positive integer. So the biggest A could be is 1 over 1, right? But that contradicts this. Sorry, I circled it in the wrong place. There we go. A can't be equal to or less than 1 and also equal to or greater than 1. So let's point that out. This contradicts the fact that A is equal to or greater than 2. Okay, therefore, if A and B are integers and A is equal to or greater than 2, then A must not divide B, or A must not divide B plus 1. And that's the end of the proof. That's a bit longer, isn't it? Does it have to be that long? I don't know. We could have maybe done it a little bit shorter if I had chosen a different wording here or there, or maybe chosen a slightly different sequence of statements. I might have been able to combine a couple of things. As it's written there, it's 11 lines. Probably could have shortened it a bit and got it in maybe about 8 lines or so, if I put some time into thinking about how could I combine a couple of things or say something a little differently. But it's not terribly long. Not at all. Okay, so there's a couple of more examples on proof by contradiction. Now, starting with the next lecture, we're going to be going into chapter 7. And we're going to start off by doing proofs of biconditionals.